Good morning, guys. Today we're going to take a look at 9.3. 9.3 is going to be a continuation of the polar coordinates that we've talked about, but it's not going to feel like it at the very beginning. Okay, we're going to apply polar coordinates to something that you've done in the past, but we're going to look at it a different way. So at the very top of your notes, you're going to see something that says Complex Numbers Review. Now, and I'm probably going to have to do a little bit of reading, so I apologize for that. So when you were in Algebra 1, Algebra 2, you learned about imaginary numbers. Okay, sometimes when we solve a quadratic, we don't get nice solutions. Okay, so x squared equals -1 doesn't have any real solutions. And we don't like that. We don't like that we can't solve an equation, because sometimes we need to be able to keep going in a problem. There's actually applications in, I want to say, electrical engineering, where imaginary numbers come up and are actually real-world solutions to problems. So it does happen, and so we've got these imaginary numbers. So I is an imaginary number, and it represents the square root of -1. Okay, so square root of -1, there are no square roots of negatives, but if you use that, we can take the square root of something like -16 by simply separating it into square root of 16, the square root of -1, square root of 16 is 4, and the square root of -1 is I. So 4I, which would be the solution to the square root of -16, that's an example of what's called a pure imaginary number. It's just an imaginary number. Imaginary numbers are part of what's called the complex number system. You've got the real numbers, you've got the imaginary numbers, and you put those all together, and that's called the complex number system. So complex numbers look like this: A plus BI. A is the real part of the number. B is the imaginary part of the number. Okay, so for example, -5 plus 6i. That's a complex number. -5 is the real part, 6 is the imaginary part. Okay, a complex number with a real part of 3 and an imaginary part of -2 would be written 3 minus 2i. Okay, now this is a number, but even though it's a number, you couldn't graph it on a number line because there's like two parts to it. Now, you can graph complex numbers, but you have to use like kind of a two-dimensional plane to do that. So you've got your x and your y axis here, but really this is our real axis. So this is a number line. This is just a normal number line you've seen since you were in elementary school. Okay, well, it's going to have negatives, so maybe since middle school. Okay, so this is the real, and this is an imaginary axis. So these are our imaginary numbers. This is 1i and 2i and 3i and -5i. Okay, that's what this is. Okay, so you can plot points just like you would coordinates. Okay, so you go out however far in the real direction, you go up the imaginary direction, and that's going to be a point that's actually a number. So that is a number, but it's in a two-dimensional space because there's two parts to it. Okay, so if I was going to plot 3 minus 2i, I'd go +3, -2, and that right there is the point 3 minus 2i. Okay, it's a point. But it's also a number. That is a number, one number. Okay, this, -4 plus 3i. -4, 1, 2, 3, 4. Go up 3, 1, 2, 3. And that's where you would put the number, -4 plus 3i. Okay, now, with numbers, we have something called absolute values. Okay, so absolute value simply means the distance from that number to 0 on a number line. Okay, so if you got a number line, so you got 0, you got 1, 2, 3, you got -1, -2, -3. Okay, 3 has an absolute value of 3 because it's 3 away from 0. -3 has an absolute value of 3 because it's 3 away from 0. That's all absolute value means, is how far is it from 0. Okay, so these two numbers that we just plotted, those have absolute values. The absolute value would just be the distance from that point back to what we think of as the origin. Okay, that's 0. That's 0 plus 0i. That's 0 on a number line. So that distance, or that distance, would be the absolute value of this. Okay, so if you look over here at this picture, you can see that any complex number, it's going to have an x direction, it's going to have a y direction. So this distance, which is the absolute value, they use z. They like to use just the letter z to represent complex numbers. So you've got this kind of two-dimensional complex number, but they just write z. For it, the absolute value of z is just, they're just using the Pythagorean theorem. Okay, so the square root of x squared plus y squared, and that would be your distance. For complex numbers, absolute value has a different name. It's also called the magnitude or the modulus. Okay, I would usually use magnitude. Magnitude, how strong is it? How far is it? Okay, so that is what that is. Now, hopefully you can kind of see that we're setting up something here. Okay, as we're talking about this distance, and we're seeing this triangle that we saw a couple sections ago, we're setting ourselves up for polar. Okay, this same point, x plus yi, can be written using polar coordinates. So this will be our r, that was hard to say. Okay, this is our r value, and then we've got this angle here that, again, if I know the x and the y, I can find that angle because that's the tangent. Okay, so that's what we're going to do. And you're going to go, okay, well, why are we doing this? There are some applications of complex numbers that are much, much easier to do by using polar coordinates instead of rectangular coordinates. And we don't have a lot of time. I usually spend an entire day just reviewing complex numbers to kind of build this up. But if you multiply complex numbers, they multiply like binomials do. Okay, if you want to take a complex number to a power, if you want to take, that number to the 4th power, it's just a number. Okay, you literally have to FOIL that out like 4 times. But there's some huge shortcuts when it comes to operations with these numbers in polar form. So that's why we do it. Okay, so down here, we're going to talk, here's the polar form of a complex number. So here's a complex number, x plus yi. That's the real part, that's the imaginary part. Well, x is r cosine theta, so we're just going to replace x with that symbol. Y is r sine theta, so you'll see r sine theta, and then there's the I, because this is the imaginary part. And then, just for simplification purposes, they kind of rewrite this. They take the r and factor it out, and you get r, and then in parentheses, cosine theta plus I sine theta. So they put the I in front of the sine so it doesn't kind of get lost in the problem. So they put the I right here. In other courses, sometimes they write this as R, I want to say it's cis theta. And that stands for cosine and then I sine. I don't do that because our book doesn't do that, but if you've ever seen that, or if you ever see that later on, that's all that is. They're just kind of abbreviating that whole thing right there. So all you need is your R, you need your theta, and you put that little CIS in the middle. Okay? That's it. That's the main thing we're going to be doing today. Okay? Alright, so first thing, writing a complex number in polar form. Alright, so we're going to take this complex number, so this is an x and this is a y, and we're going to rewrite it in polar form, which means I need an r and I need a theta. Well, we did this before. R is the square root of x squared plus y squared. Theta is the inverse tangent of y over x. Unless our x is negative, and then we'll also have to add pi to it to get it into the right quadrant. So when I have this value, this is my x is radical 3. This is my y. My y is -1. Okay, it's the number part. That's your imaginary part. So r is the square root of radical 3 squared plus -1 squared, which is the square root of 3 plus 1, so 2. So there's our r. Now we're going to do our theta. So inverse tangent of negative 1 over radical 3. So negative 1 over radical 3. Now that's really negative radical 3 over 3. Okay. Now, if you've got your chart handy, okay, radical 3 over 3, the angle's pi over 6. Now this is a negative, so it's going to be negative pi over 6. So inverse tangent of negative radical 3 over 3 is negative pi over 6. We're not going to add pi to this because our x value is positive, so that's the angle we want. So now all we have to do is write it. 2 cosine of negative pi over 6 plus I sine of negative pi over 6. And that's our answer. That's it. Okay, how about the other direction? So going from polar form to rectangular form. This is real easy. All you do is simplify this. Okay, do the math. So inside these parentheses, I have the cosine of 60. Well, cosine of 60 is 1/2 I. And then the sine of 60, well, the sine of 60 is radical 3 over 2. And then I can distribute the negative 3 in. So it's going to be negative 3 over 2 plus, and then negative 3 times, well, not a lot of simplifying that's going to happen here. So this is going to be negative 3 radical 3 over 2I. That's it. You're done. By simplifying this, by doing the math, you've converted the polar form into an x and a y. That's your answer. That's it. Okay? Now, last couple things. Down here, this is a way, these are formulas for multiplying and dividing. Okay? Multiplying complex numbers isn't super hard. You just got to FOIL the numbers out. Dividing is kind of ugly. Dividing complex numbers, you really are multiplying by conjugates and you're doing all kind of ugly things. Let me show you what happens in polar form. Okay, so I've got two numbers. I've got Z1 and I got Z2. So those are my two numbers. And here's how they're written in polar form. So they both have an R out front. They have the cosine of an angle plus I sine of the angle. Okay? To multiply, so Z1 times Z2. You literally multiply the two R's together. You add the two thetas together. And you are done. Okay? That's it. That's all you do. To divide two numbers in polar form, you divide the R's, you subtract the thetas, and then you're done. Okay? So literally, if I've got two numbers, so here I wrote them as Z and W. So I got two numbers. Z times W is literally 8 times 2, 16. 40 plus 20, 60. Cosine of 60 plus I sine of 60. My directions say to leave in polar form, so that means I'm done. That's literally the answer. Okay? If I said to rewrite it as in rectangular form, then we could just do the cosine of 60, do the sine of 60, distribute the 16, and then we'd be done. Okay? Z over W. Okay, so we're dividing. We're dividing this by this. So we are going to divide 8 by 2. That's 4. We're going to subtract 40 and 20. So that's 20. And we're going to get the cosine of 20 plus I sine 20. Super easy. Okay? What about the other direction? What about y over z? Well, if we're dividing y by z, then the order that we're going to do things is also flipped. We're going to take 2 divided by 8. Okay, that's 1/4. That's okay. And we're going to take 20 minus 40, so that's negative 20. That's okay. So cosine of negative 20 plus I sine of negative 20. I apologize for the tunes. It's the passing period, so it happens. All right, and that's it. That's your answer. That's what we're doing today. Okay, so I just needed to introduce complex numbers, how to write them in polar form, and then how to multiply and divide. Okay, next class is going to be a little more interesting than that. All right, take a look at your worksheet. Let me know if you got questions.